This episode is brought to you by Brilliant. In 2022, it's estimated that around 1.2 trillion gallons, or about 4.5 trillion liters of gasoline, was consumed worldwide. This is roughly equivalent to the amount of energy released by 745 Tsar Bomba detonations, the most powerful nuclear weapon ever detonated. Gasoline production accounts for almost 45% of total global oil consumption, and alongside diesel fuel, it forms the energy backbone for the vast majority of ground transportation on Earth. While today gasoline is a fundamental ingredient to the global economy, almost a century and a half ago it was seen as a useless byproduct of early oil refining. For much of the second half of the 19th century, the primary goal of oil refining was to produce kerosene, primarily for use in lamps and stoves. Early refining was accomplished using fractional distillation, a process by which the crude oil is heated at high temperatures to create a rising vapor within a still called a fractioning column. Because lighter and more volatile compounds rise to the top of the still, while the heavier ones settle to the bottom, the still separates the crude oil's constituent hydrocarbon components by their relative boiling points, by allowing them to collect fractionally at different temperature zones within the column. Gasoline is a mixture of light hydrocarbons with relatively low boiling points that at the time had no significant commercial value and was even seen as dangerous due to its high volatility. Because of this, it was initially considered a waste product and was often discarded and simply burnt off. In fact, the term gasoline was initially coined to describe distillate oils that vaporize into a gas easily. The term would soon find itself being used as a generic description for any volatile lighting oils. Both cazoline and gasoline were even contended trademarks for such products in the 1860s. Within a decade, the term petrol, short for refined petroleum, began to grow in popularity in British Commonwealth countries, with its first description in print as the material employed to run engines appearing in 1895. In the 1880s, the development and subsequent success of the Otto cycle engine directly led to a demand for a volatile fuel source that could power them practically. Initially, coal gas, a gaseous mixture composed of hydrogen, methane, and carbon monoxide, produced by the continuous heating of coal in the absence of air, was used as a fuel source for early designs, though these engines would quickly be adopted to a more practical liquid fuel source using a carburetor. These early surface carburetors relied on evaporation from the surface of the liquid fuel to form a combustible mixture with incoming air. For this to work efficiently, a volatile hydrocarbon fuel that would vaporize around the operating temperatures of the engine was needed. Gasoline would prove to be the ideal fuel for this. By the 1880s, the introduction of the float-fed carburetor design, which used an atomizer nozzle, allowed for even more fueling flexibility. This made these engines far more reliable and robust, as they could now easily run on the loosely defined composition of early gasoline. Now intertwined with the success of the Otto cycle engine, this once useless byproduct of oil refining would now experience a huge surge in demand as the internal combustion engine became a foundational element of 20th century technological development. Despite its public perception, gasoline is not a clearly defined compound, but rather a homogenous blend of light to medium molecular weight hydrocarbons, ranging from 4 to 12 carbon atoms per molecule. Its definition comes from its properties as a fuel, and its exact composition can vary based on the region of use, feedstock, and the processes used to create it. The hydrocarbon types that commonly combine to form gasoline and contribute to its properties as a fuel are paraffins, olefins, naphthenes, and aromatics. Paraffins, also known as alkanes, are the most prevalent hydrocarbons in gasoline. Alkanes are saturated hydrocarbons, meaning they do not have any double or triple bonds, and they contain relatively large reserves of energy. Examples of paraffins in gasoline are butane, pentane, and hexane. Olefins, also known as alkenes, are hydrocarbons that contain at least one carbon-carbon double bond and are unsaturated, meaning they can react with other chemicals to form new compounds. Examples of olefins commonly found in gasoline include ethylene and propylene. Naphthenes, also known as cycloalkanes, are hydrocarbons that contain one or more cycloalkane ring and are saturated. Saturated hydrocarbons tend to be relatively inert and do not undergo additional reactions easily. Aromatics are unsaturated hydrocarbons that contain one or more aromatic rings, which are six-membered carbon rings with alternating double bonds. Common examples of aromatics found in gasoline include benzene, toluene, and xylene. The relative proportions of these different types of hydrocarbons in gasoline have a significant impact on its properties, with octane rating and energy content being two key metrics. Depending on the blend, gasoline can vary anywhere from 32 to 36 megajoules per liter, with an octane rating that can vary from unusable for engine use to ratings designed for high compression performance and aviation engines. Octane rating is a measure of a fuel's ability to resist knocking or pinging during combustion. This phenomenon is caused by the air-fuel mixture detonating prematurely within the engine and can cause engine damage, reduced power output, and increased emissions. This measurement system was originally developed based on the properties of isooctane, a hydrocarbon compound that is very resistant to knocking. Isooctane was assigned a rating of 100 as it provided the highest known level of knock resistance at the time. Modern octane ratings are typically expressed in one of two forms: research octane number or RON and motor octane number or MON. RON is a measure of a fuel's ability to resist knocking under mild driving conditions, while MON measures its resistance to knocking under more severe conditions, such as high engine speeds and loads. The two numbers are averaged to give the fuel's anti-knock index, or AKI, also known as the pump octane number, or PON, which is the number typically displayed on fuel pumps in the United States. The higher the octane rating, the more resistant the fuel is to knocking. Fuels with octane ratings as high as 115 to 150 MON are typically used in high-performance engines or engines with higher compression ratios, such as in aviation where the risk of knocking is greater. Early gasoline produced directly from distillation was known as straight-run gasoline. Its composition varied wildly as the mixtures and ratios of the hydrocarbon blend produced was often unknown and highly dependent on the source of the crude oil and the specifics of the refining process used. These fuels were characterized by their higher proportion of naphthenes over other hydrocarbons, as well as higher amounts of sulfur and nitrogen. When gasoline containing sulfur is burned, it forms sulfur dioxide and sulfur trioxide, which creates deposits within an engine and are major contributors to air pollution, while the nitrogen-containing compounds produce nitrogen oxides when combusted, which are a major contributor to smog, acid rain, and ground-level ozone. At the time, the effects of abnormal combustion and engine knock resistance were not yet established. A fuel's volatility via its boiling point was used as the primary metric of its performance. Early fuels that had relatively higher boiling points and overall lower volatility were known as high-test gasoline and were primarily used on aircraft engines. These early gasoline blends by today's standards would be unusable in the higher compression engines of today, as even the most high-test blends would have an octane rating below 70, with lesser quality blends going as low as 40. By 1910, the rising demand for automobiles combined with the expansion of electrification created a flip in the product demands of the petroleum industry, with the need for gasoline now beginning to supersede that of kerosene. In response to this supply problem, the industry looked to a technique known as thermal cracking to increase the yield of gasoline from the heavier hydrocarbons. First conceived by Russian engineers Vladimir Shukov and Sergei Gavrilov in 1981, a variant of the technique would be developed by American engineers William Marion Burton and Robert E. Humphrey in 1908. Coined the Burton process, this technique thermally decomposed straight-run gasoline and heavier oils at temperatures between 370 and 400 degrees Celsius, or 700 to 750 degrees Fahrenheit, and under a pressure of around 620 kilopascals, or around 90 psi, cracking the heavier hydrocarbons and depleting their hydrogen to produce more lighter, hydrogen-rich hydrocarbons. This enabled refiners to produce cracked naphthenes and other light oil products, which overall reduced the proportion of heavy oil produced during refining. As the First World War raged on, a troublesome issue emerged with the usage of gasoline in aviation. The broad range of fuel volatility and octane ratings available posed a significant threat to aircraft engines, as they would produce unpredictable levels of power, risking the safety of early, power-sensitive planes during takeoff. Adding to this danger was the unavailability of consistent high-octane fuel, which limited engines to heavier, lower compression designs. The instability of fuel was also a concern, as the higher levels of unsaturated hydrocarbons produced by thermal cracking were reactive and prone to combining with impurities, resulting in gumming, further exacerbating the problem. Spark plug fouling and oil dilution was also occurring with thermally cracked gasoline due to volatility inconsistencies. This prompted the US Army to conduct research on gasoline properties and its effect on performance, with the results leading to the first US government specifications to be published for gasoline in 1922. Designated as fighting and domestic grades for aviation and motor grades for automobiles, these specifications defined fuel grades by their boiling points, color, sulfur content, and susceptibility to gum formation. Around this time, the automotive industry was increasingly growing dissatisfied with the oil industry's quality issues and began to conduct their own research into the effects of thermally cracked gasoline on abnormal combustion. In 1921, Charles F. Kettering of General Motors, upon investigating additives to improve fuel performance, ultimately looked towards tetraethyl lead as the solution. Tetraethyl lead was the product of research previously conducted by engineers Thomas Midgley Jr. and Thomas Boyd on abnormal combustion, and it would become the defining component of leaded gasoline. When tetraethyl lead is added to gasoline, it dissociates into its component parts of lead ions and ethyl radicals. These ethyl radicals react with other gasoline molecules to form branched chain hydrocarbons that have a higher resistance to combust prematurely under pressure, effectively increasing the octane rating of the gasoline. Despite warnings about the dangers of leaded compounds, Kettering secured a patent for tetraethyl lead and would promote it. Even amid instances of lead poisoning among workers in production plants and a ban on sales in several areas, flawed industry-funded studies claiming that leaded gasoline was not a public health issue and was the only viable additive that prevented engine knocking without affecting fuel economy removed the barriers to its eventual mass adoption by the 1930s. In the early 1920s, Almer McDuffie of the Gulf Refining Company would develop a new refining process that could potentially triple the gasoline yielded from crude oil by existing distillation methods. Known as catalytic cracking, the process heats heavy hydrocarbon feedstock to a high temperature along with a catalyst in a reactor. The catalyst initiates a series of chemical reactions that break the hydrocarbon molecules apart into smaller fragments that are then further cracked and recombined to produce lighter, more desired hydrocarbons for gasoline. Initially, the McAfee cracking process required anhydrous aluminum chloride, which proved to be prohibitively expensive for widespread use. By the early 1930s, French mechanical engineer Eugene Jules Houdry, backed by the Sun Oil Company, known today as Sunoco, would begin his own research into a commercially viable catalytic cracking process. In 1938, the Houdry process would be publicly introduced. The Houdry process uses a fixed bed reactor filled with small beads of a catalyst, typically made of alumina or silica alumina. The heavy hydrocarbon feedstock is mixed with steam and passed over the catalyst bed at a temperature of around 538 degrees Celsius or about 1,000 degrees Fahrenheit. The high temperature and pressure causes the hydrocarbon molecules to break apart into smaller fragments, which then react with each other to form lighter hydrocarbons suitable for gasoline. One of the key innovations of the Houdry process was the use of a regenerative catalyst, which could be periodically regenerated to restore its activity. This was achieved by burning off the carbon deposits that accumulated on the catalyst during the cracking process in a step known as catalyst regeneration. Initially, the Houdry process operated in batches where refining and regeneration alternated. However, a technique called thermophore catalytic cracking would be developed that used a bucket conveyor elevator to move the catalyst from the regeneration kiln to the separate reactor section, creating a continuous operation. Catalytic cracked gasoline had a significantly higher olefin content and more branched chain and aromatic hydrocarbons than thermally cracked gasoline, which raised its octane rating. The catalyzing action also produced a fuel with lower sulfur and nitrogen content. The advent of catalytic cracking rendered thermal cracking obsolete, and over the next few decades, it would be completely phased out as a primary process. It's speculated that the combination of the larger yield of the Houdry process, along with the higher octane ratings created by tetraethyl lead, were key factors in the winning of World War II, especially when it came to fueling the higher power aircraft engines towards the later years of the war. In an attempt to circumvent Houdry's patents, Standard Oil began researching an alternative method to catalytic cracking, resulting in the development and fielding of the fluid-based catalytic cracking process in the early 1940s. Initially conceived by Warren K. Lewis and Edwin R. Gilliland at the Massachusetts Institute of Technology, fluid catalytic cracking used a catalyst suspended in the form of fine particles within the reactor to improve the efficiency and effectiveness of the cracking process. As the catalyst became deactivated by the buildup of carbon deposits caused by the cracking process, the spent catalyst is separated from the cracked hydrocarbon products and sent to a regeneration unit where the contaminants are burnt off, and the catalyst is reactivated for reuse. Fluid catalytic cracking allowed for better control over the reaction and produced a more consistent, higher yield of gasoline. It was also continuous in nature and relatively easy to maintain. This efficiency and versatility would lead to fluid catalytic cracking becoming one of the most popular oil refining processes used today. By the 1950s, as automobile engines continued to develop and become more powerful, the demand for higher octane gasoline grew. High quality control of gasoline production combined with an increase in the use of tetraethyl lead brought typical octane ratings up to around 70 to 80 RON, with premium grades reaching 90 to 95 RON or even higher in some cases. Additionally, the petroleum industry saw significant advances in catalytic reforming technologies that were first commercialized in the 1940s for increasing the octane rating of gasoline. Catalytic reforming works by converting low-octane naphtha into high-octane aromatic compounds such as benzene, toluene, and xylenes through the use of a catalyst, typically platinum or a platinum-rhenium combination at elevated temperatures and pressures. The resultant reformate is then used as blending components in gasoline to boost its octane rating. The 1950s also saw the military's transition from piston to jet aircraft, reducing its demand for a high-octane aviation gasoline in favor of kerosene-based jet fuels, realigning the focus of gasoline refining research to a much larger commercial scope. During this time period, a new type of catalytic cracking process based on decades of research on hydrogenation, a reaction where hydrogen was used to break down large hydrocarbon molecules into smaller ones while adding hydrogen atoms to the resulting molecules. This research would yield a process known as hydrocracking, a technique that combines hydrogen and a catalyst under high pressure, usually between 70 to 200 bar, and high temperatures in the presence of hydrogen gas to break down large hydrocarbon molecules into smaller, more desirable ones. The breakthrough that made this possible was the development of catalysts composed of metals like platinum, palladium, nickel, and molybdenum, supported on a solid material like alumina or silica that made the process viable. Hydrocracking produced high-quality, cleaner-burning fuels with low sulfur and nitrogen content. It was very flexible, allowing for variations in the operating conditions and catalysts, while producing a high yield of gasoline from a wide range of feedstocks, including heavy oils and residues from other refining processes. Its efficiency at producing higher yields of gasoline from heavier oil products led to it being adopted on a commercial scale by refineries around the world during the 1960s. Since its commercial adoption in the 1940s, the harmful effects of lead exposure from gasoline were becoming apparent, with studies linking atmospheric lead emissions to various health problems, including neurological damage, particularly in children. However, by 1970, the United States Environmental Protection Agency would be established, with one of its first tasks being to address the growing concerns about lead pollution. That year, the second of two acts that formed the Clean Air Act would be passed, giving the EPA authority to regulate the use of lead additives in gasoline. Within 3 years, the EPA would introduce regulations to gradually reduce the amount of lead in gasoline in a phase-down process that started with a reduction of lead content to 2 grams per gallon in 1973, followed by further reductions to 1.7 grams per gallon in 1975, 1.1 grams per gallon in 1978, and finally 0.1 grams per gallon in 1986 for on-road vehicles. By the 1990s, the sale of leaded gasoline for road vehicles was effectively banned in the United States, with only a few exceptions for off-road use and aviation gasoline, though at only 0.05 grams per gallon. Following the US's lead, many countries around the world implemented their own regulations to phase out leaded gasoline, and by the early 2000s, leaded gasoline was virtually eliminated in most developed countries. By 2011, Algeria, the last remaining country to use leaded gasoline, would end its use, finally completing the global elimination of leaded gasoline use for road vehicles. After the phase-out of lead additives in gasoline, the petroleum industry had to find alternative ways to maintain and improve the octane rating of gasoline. One class of additives, called oxygenates, became a popular solution. Oxygenates are oxygen-containing hydrocarbons that promote more complete fuel burning within the engine, while also increasing the resistance of the fuel to auto-ignition, improving engine performance. When blended with lower octane gasoline, they dilute the lower octane components, increasing the overall octane rating. The primary oxygenate types used are alcohols and ethers, with ethanol and methyl tertiary butyl ether, or MTBE, being the most popular choices. MTBE in particular, which was derived from natural gas and had an octane rating of 110, played a significant role in the phase-out of lead additives in gasoline. However, MTBE use had declined significantly over the past 2 decades due to environmental concerns. Its high solubility in water leads to leaks from underground storage tanks and gasoline spills, causing the contamination of groundwater sources, affecting the taste and odor of drinking water. Ingesting water with high concentrations of MTBE can also cause adverse health effects, such as headaches, nausea, and irritation of the respiratory system. The phase-out of MTBE led to ethanol becoming the primary oxygenate and octane booster in gasoline by the early 2000s. At an octane rating of 109 RON, ethanol is typically blended with gasoline in varying proportions. In the United States, the most common blend is E10, which contains up to 10% ethanol and is compatible with most gasoline-powered vehicles. E15, containing up to 15% ethanol, is generally compatible with most vehicles made within the last 20 years. Flexible fuel vehicles can run on gasoline with higher ethanol content, such as E85, which contains up to 85% ethanol. Ethanol is produced from renewable biomass sources, which helps to reduce the reliance on non-renewable fossil fuels. In concept, the use of ethanol in gasoline can help to reduce greenhouse gas emissions, as the plants used to produce ethanol absorb carbon dioxide during their growth. It also promotes the agricultural sector, creating jobs and encouraging investment in the biofuel industry, though there are concerns about its potential impact on food prices due to competition. Beyond additives, the process of alkylation also grew in its use to boost octane ratings. This technique is used to produce alkylates, a high-octane blending component for gasoline. Alkylation starts with mainly isobutane and light olefins that are obtained from other refining processes. They're first treated to remove impurities such as sulfur, nitrogen, and water, and then mixed with the acid catalyst and fed into an alkylation reactor. In the reactor, the olefinic hydrocarbons react with isobutane to form larger, branched alkylated hydrocarbons. Much like other catalytic processes, the acid catalyst is separated and recycled, while the alkylates are separated and unreacted isobutane recycled. The high-octane alkylates is then blended with other gasoline components. Another similar catalytic technique that began to grow in popularity is gasoline isomerization. This process typically focuses on the conversion of low-octane straight-chained paraffins found in light naphtha into branched-chained hydrocarbons that have a higher octane rating. Much like with alkylation, the feedstock is first treated to remove impurities such as sulfur, nitrogen, and water. Then it is mixed with hydrogen and passed through a fixed bed reactor containing a catalyst at moderate temperatures and pressures. In the reactor, the straight-chained paraffins react with the catalyst to form their branched-chained isomers. These isomers are then separated from the unreacted feedstock and byproducts, and are then blended with other gasoline components to produce a final gasoline product with a higher octane rating. Today, gasoline production is based on a complex combination of refining processes that focus on cleaner, more environmentally friendly fuels. Modern refineries employ a variety of refining sequences that combine catalytic reforming, alkylation, hydrocracking, and isomerization to produce high-octane gasoline components that must not only meet increasingly stringent emission standards and meet performance requirements, but also work well within the seasonal climate of the target region of consumption, as well as meet the anticipated consumer demand. While modern petroleum refining is fundamentally based in organic chemistry, the operation of the industrial processes that perform each stage of the requisite reactions are controlled by industrial electromechanical technologies. These systems must both perform the needed instrumentation and automate the entire refining sequence, with algorithms driving the entire process. Have you ever wanted to build a solid foundation for understanding how algorithms form the backbone for the vast majority of the industrial technologies we rely on? That's where Brilliant.org comes in. Brilliant is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. Brilliant is constantly developing their courses to offer the most visual, hands-on approach possible to make mastering the key concepts behind today's technology effective and engaging. I found their computer science courses to be extremely valuable, and it allows you to develop, examine, and self-discover the key concepts of algorithm design through the eyes of real-world applications using interactive exercises. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. To try everything Brilliant has to offer free for a full 30 days and start learning STEM today, visit brilliant.org/newmind or click on the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription.